All right, so let's talk about orbital diagrams. So we said that all electrons have to have 4 different quantum numbers, which tells us where the electrons are, or the best probability of finding where the electrons are. So let's see how we organize all of the electrons in an atom. Let's just start with atoms. So we are talking about, this is the orbital diagrams. Remember the orbitals, this is where the electrons live because the electrons are orbiting the nucleus, and the nucleus is where the protons and neutrons are. So we're talking about electrons, and remember, if you're talking about an atom is charge neutral, which means the number of protons equals the number of electrons. You have the same number of positive charges as negative charges. So also remember what we know about the number of protons. This is the atomic number. This is the number on the periodic table, which tells us the identity of the atom. So whatever number on the periodic table the element is, that's how many electrons you have. And then we're going to use the orbital diagram to see where that many electrons are going to be. So the first thing that we need to talk about is something called the Aufbau principle. What the Aufbau principle says is that the building of the electron configurations will add 1 electron at a time, and it will always fill the lowest energy level first. So I'm going to say filling of electrons into lowest energy levels first. So you'll see what I mean here in a second. So there is a specific order for what's called the electron configuration. So that's a word that you're going to hear again and again. So we're going to talk about the orbital diagrams and something called the electron configuration, which is exactly what it sounds like. It's the configuration of the electrons. It's where all of the electrons are. So the order for electron configuration comes from the way the periodic table is set up. So instead of drawing it out for you, I'm just going to show you what it is, what it looks like in your textbook. So this is on page 109 of my textbook. I might have the first edition here with me. So it should be in section 3.8 of whatever version of the textbook that you have. But you can see how there's 3 different colors here. These are called different blocks, and these are for the different orbitals. These are for the different L orbitals. So remember, N is the energy level. So that's going to be written down the side here. 1, 2, 3, 4, 5, 6, 7. And then the colors, the letters, have to do with L. So if L is 1, then that is the S orbital. So here you see 1s. Helium you see is over here. It should be hydrogen and helium. These are kind of anomalies on the periodic table. They don't really fit anywhere. We put hydrogen here and helium here. And then next we have, so this is 1s, and there's room for 2 electrons in here. 1, 2. And then we have 2s. There's room for 2 electrons here. 1, 2. And then, so it goes in this order. So you see if you follow the arrows up here, see if you can see this. Yeah. So it goes from 1s to 2s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. So this is the order of the electrons as they fill this orbital diagram, or it is their electron configuration. We are not going to do anything down here on the periodic table with this F orbitals. These are called the lanthanides and actinides. There won't be any examples of these for anything that we do for this quarter. So I'm not even going to worry about explaining these. But what you need to know is the s orbitals here, they can hold 2 electrons. The p orbitals here, they can hold 6 electrons. And then the d orbitals here, they can hold 10 electrons. So we are going to make a line for each pair of electrons. So the s orbital is going to have one line because two electrons can go in each orbital. Because remember from our quantum numbers, remember m sub s can be plus 1/2 and minus 1/2, spinning opposite directions. So those 2 pairs of electrons can go on each space. So s, you're going to see 1 line, but 2 electrons. P, you're going to see 3 lines, but 6 electrons. D, you'll see 5 lines for 10 electrons. So I'm going to write some of that out, but you can definitely refer back to that as we're going. So the s orbital holds 2 electrons, and it looks like this. And you'll either see it written like this, 1, 2, or you'll see it written like this, 1, 2, with the arrows spinning opposite directions. The arrows going opposite directions represents the electrons spinning in different directions. I'm going to use this representation because this is what your textbook uses, but if you happen to look this up somewhere else and you see X's instead of arrows, it's the same thing. Okay, so the s orbital holds 2 electrons. The p orbital holds 6 electrons, so it's going to look like this, 1, 2, 3, and then it would go 1, 2, 3, 4, 5, 6. So that's the 6 electrons in the p orbital. The d orbital holds 10 electrons, so that's going to mean 5 dashes. Eight, 9, 10. And then the f orbital, which we are not going to do any examples of, but it holds 14 electrons. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So maybe you noticed something that I was doing there as I was filling those electrons. You have to fill each of the blank spaces before you can go back and double up. This is called Hund's rule. I'll put that over here. Hund's rule says that the lowest energy electron configuration is the one with the maximum number of unpaired electrons with the same spin. So maximum number of unpaired electrons within that orbital. So I'll give you a quick example of that. So let's say, let's just look at carbon. So carbon is number 6 on the periodic table. So it's number 6 on the periodic table. This number 6 means that's the number of protons. And because this is the carbon atom, the number of protons equals the number of electrons. So we are trying to see where are these 6 electrons going to be. And I know that carbon has 6 electrons because it's number 6 on the periodic table. Number 6 means there's 6 protons, and because this is a charged neutral atom, if I have 6 protons, I have 6 electrons. So let's just look at how this would go. So back from your textbook, if you look, it tells you the order of these orbital diagram. 1s, I'm going to put 1 dash. 2s, I'm going to put 1 dash. 2p, I'm going to put 3 dashes. So you could write this whole thing out. I know I only need 6 electrons, so I'm just going to stop here, but you might see this written all the way out for other examples. So now I'm just going to start counting, and I'm going to fill in 6 electrons. So each of these single-sided arrows represents 1 electron. Remember, we're going to fill from the lowest energy levels first, and we want the maximum number of unpaired electrons. So this is what it would look like. I'm counting to 6. 1, 2, 3, 4, 5, 6. This is the orbital diagram of carbon. This is where the 6 electrons of carbon are. 2 electrons are in the 1s orbital, 2 electrons are in the 2s orbital, and 2 unpaired electrons are in the 2p orbital. This is correct. What is incorrect is if I had written it like this, if I counted to 6, 1, 2, 3, 4, 5, 6. This would be wrong because remember Hund's rule said that we want the maximum number of unpaired electrons. We have to fill each of these spaces before we go back and double up. So this is wrong. This one is correct. We always go from lowest energy level to highest, and we always want to spread out the electrons into individual orbitals before we go back and double up. So that's the rules, that's the gist of this. Let's do some more examples. So let's look at bromine. Bromine is number 35 on the periodic table. It's Br. So this is just the inside of the textbook. Here's bromine right here, Br. It's number 35. So that means I'm going to draw the orbital diagram for bromine and see where these 35 electrons are. Again, I know there's 35 electrons because this is number 35 on the periodic table. The number on the periodic table is the atomic number. It tells me how many protons there are. The bromine atom is charged neutral, which means it also has that many electrons. So let's draw the orbital diagram for bromine. And again, the order that the orbital diagram goes comes from this page where it shows you that order. So it's going to go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. So I see that bromine right here is in this 4p block. So that tells me how far I'm going to have to go. I'm going to need everything up until 4p. So I can stop at 4p. I don't have to write all of these. So that's a clue to tell you how to do that. I know this orbital diagram just because I've done it so many times. You might have to refer to something like this while you're writing out the orbital diagram. Okay, so I'm going to go ahead and write this out. I'm going to put it right here in the middle. So I'm going to do bromine. So again, this is number 35 on the periodic table. Protons equal electrons in a charge neutral atom. So I need to find out where are these 35 electrons. So I'm going to write out the orbital diagram, which looks like this. 1s, one line. 2s, one line. 2p, 3 lines. 3s, 1 line. 3p, 3 lines. 4s, 1 line. 3d, 5 lines. 4p, 3 lines. So again, I knew to stop at 4p because when I look at bromine on the periodic table, I see that it's in that 4p block. So this is how many orbitals I'm going to need to house all of these electrons. Okay, so let's start counting. So you're just counting to 35. That's all you're doing. And I'm going to do the double-sided arrows. So here I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. So this is the orbital diagram for bromine. Now it doesn't matter where the location of this unpaired electron is, just that you understand Hund's rule says that we have to have as many unpaired electrons as possible before we start doubling up. This is just as correct as if you had a pair here and then you had an unpaired over here. The position of them within the orbital is not important. So this is called the orbital diagram. So this is not the only way that we represent where all of these electrons are. There's different ways to do it. This is called the orbital diagram. From the same thing, let's look at something called the electron configuration, which is when we're going to write it out. But I'm still going to use bromine. So I'm going to say bromine electron configuration. So this electron configuration notation is written out without showing all of these dashes, and we show the number of electrons in each of these orbitals with superscripts, which are like exponents. So I'm going to write this out, 1s2, and again, this 2 right here comes from these 2 electrons, 1s2, 2s2, 2 electrons, 2p6, because there's 6 electrons, 3s2, 3p6, 4s2, 3d10, and then 4p, 1, 2, 3, 4, 5. So this is the electron configuration for bromine. It's just a different way to represent the same information. If you were to add up all of these superscripts, it would equal the number of electrons. So if you added all of these numbers together, it would equal 35. So this is just the regular expanded full electron configuration. There's another way to note it that is more abbreviated, and that is called the noble gas configuration. So what the noble gas configuration is it's an abbreviated form of this because, you know, the periodic table goes up pretty high. This is only number 35 with bromine, but if you were doing something that had 100 electrons in it, you could see that this would be a big mess. It would just be a lot of unnecessary writing. What the noble gas configuration is it's an abbreviated form of the complete electron configuration where it goes, it's the electron configuration from the previous noble gas. So remember when we broke down the periodic table in chapter 2, and we said everything that's in group 8 over here, these are the noble gases. So these are kind of like the placeholders. So what we're going to do is we're going to say, what's the previous noble gas to bromine? Not what is the nearest noble gas. The nearest noble gas to bromine right here would be krypton. That's not what we want. We want the previous noble gas, which is argon. So the way that we write the electron configuration is we write the previous noble gas, which here is argon. You put it in brackets. So what this means here is this means this represents all of the electrons up until this point of argon. So it's like writing all of this out and stopping here. So now to get to bromine, I pretty much just start at the next energy level. So it covers everything from 1s to 3p, and then I'm just going to start here. So the noble gas goes everything to here for this example. So then I'm just going to write the rest. So usually there's a colon there, and then we go from where we left off. So it's going to be argon 4s2 3d10 4p5. So this noble gas configuration, again, it's just an abbreviation, because if you were to write the the electron configuration of something with 80 or 100 electrons, this would just be a lot of information. So the noble gas always shows you, it's a condensed, abbreviated version. So essentially it's everything from here to here. This is argon. And now we're just looking at what's past that for the noble gas configuration. We will look at some more examples of these. You'll definitely see something on the exam where it will ask you to write the orbital diagram, the electron configuration, and the noble gas configuration for an element. And again, these are where the electrons are. They're starting in the lowest energy level, and then they're filling the whole orbital with one electron before they go back and double up.